On the afternoon of December 5, 1945, 5 U.S. Navy Avenger bombers took off from the coast of Florida. The weather was clear, and the 3-hour training mission over the Atlantic was completely routine. 2 hours into the flight, the squadron leader, a highly experienced pilot with thousands of hours in the air, radioed base with a serious problem. His compass had stopped working. Over the radio, base operators could hear the panic setting in among the 14 crew members. They pulled out backup compasses, but those were malfunctioning too. The pilots were flying blind over the open ocean, unable to tell east from west. By nightfall, all 5 bombers were gone. The Navy immediately scrambled a massive search and rescue plane with a 13-man crew to find them. Within 30 minutes of takeoff, that plane exploded in midair. 27 men died, and not a single piece of wreckage was ever found. This tragedy gave birth to the legend of the Bermuda Triangle. But dismissing ghosts and sea monsters leaves us with a terrifying scientific question. What specific environmental mechanisms are capable of plucking an entire squadron of aircraft right out of the sky? The first major suspect is the exact mechanism that doomed Flight 19, geomagnetic interference. Deep underground, extreme temperature differences cause liquid metal to churn. This action turns the Earth into a massive electrical generator that projects an active, constantly moving magnetic field. The Bermuda Triangle happens to sit squarely in a highly active zone, where the magnetic fields of the northern and southern hemispheres meet and clash. Because of this intersection, the localized magnetic field fluctuates. A compass needle here might point toward true geographical north, or it might be pulled severely toward magnetic north, and that variation changes without warning. These invisible magnetic shifts create a physical trap for aviators and sailors. Relying on an uncorrected analog compass in this convergence zone instantly strips a pilot of their spatial awareness, turning a minor navigation error into an unrecoverable flight path out over the open Atlantic. Magnetic fields explain navigation failures, but they do not explain how ships and planes physically sink. For that, we have to look down at the ocean floor, where vast deposits of natural gas hydrates are buried deep in the sediment. When the seabed is disturbed by an underwater sediment slide, these deposits can fracture, triggering the sudden, violent release of highly compressed methane gas. In the water, this massive eruption of bubbles lowers the density of the ocean so drastically that ships lose their buoyancy and sink. But the danger doesn't stop at the surface. The methane plume breaches the water and continues ascending straight into the sky. If an airplane flies through this invisible gas cloud, the chemistry is devastating. The methane instantly starves the plane's air-aspirated engines of oxygen, choking the combustion cycle. A mysterious vanishing act can actually be the result of a sudden, invisible chemical disruption that physically drops a machine into the ocean. Then there is the baseline meteorology. The warm waters of the Gulf Stream flow directly through this region, feeding incredibly volatile, fast-moving weather systems. These extreme conditions frequently spawn independent megastorms. These are highly energetic storm cells that go beyond standard hurricanes, acting as massive generators of charged atmospheric particles. Whether channeled down from space weather or drawn up from radioactive radon gas leaking out of the seabed, these charged particles hyper-ionize a localized column of air directly beneath the storm. Entering this highly conductive air is incredibly dangerous for older aircraft. The static saturation causes coronal arcing, electricity jumping across unshielded high-tension wiring, physically shorting out piston-driven engines. Pilots call this an electronic fog. It acts like a naturally occurring electromagnetic pulse, blinding navigation instruments and killing engine power, all while trapping the aircraft inside hurricane-force winds. With extreme magnetic shifts, methane eruptions, and hyper-ionized megastorms all present, the region is undeniably dangerous. But why is this specific patch of the Atlantic considered uniquely deadly compared to the rest of the world? This chart compares the raw volume of ship and plane traffic against the percentage of actual disappearances across the world's oceans. When you look at the hard data collected by the U.S. Coast Guard and NOAA, the rate of missing vessels in the Bermuda Triangle is completely average. There is no statistical anomaly. To understand the discrepancy between the data and the myth, we have to look at cognitive science, specifically observational selection bias. Once you learn about a phenomenon, you start noticing it everywhere. while ignoring everything else. In the 1960s, a magazine article officially coined the term Bermuda Triangle. Suddenly, the media hyper-focused on any accident in the specific region. Identical storms and natural disasters occurring in the Pacific or the Indian Ocean were simply ignored, heavily skewing the public's perception. Looking at the mapped flight path of Flight 19 through this lens, the mystery dissolves. It was a textbook tragedy: analog instrument failure, brutal weather, and a disoriented pilot who ignored his crew, flying an eastern heading into the Atlantic until fuel ran dry. The ocean is a complex system of severe fluid dynamics, volatile meteorology, and vast distances. It is a naturally hostile environment that requires absolutely no supernatural assistance to be deadly.